We're going to talk about EM today. The discussion in the book is fairly simple. I'm going to discuss it a little bit differently, but I encourage you to read the book as well. Thank you, Rebecca. We're going to start. So EM is all about maximum likelihood, finding maximum likelihood solutions under some situations when they're not easy to find. We're going to start with a situation where maximum likelihood solution is easy to find, just to kind of refresh your mind and see where things go wrong. So let's start with just a simple Gaussian. Let's say you're told the data is generated by a Gaussian, and further you're even told what the standard deviation of the Gaussian is. It's fixed. So you only need to find the mean of the Gaussian, and we're looking for the maximum likelihood solution, and I believe this was in your homework. So we're going to assume, call it like one Gaussian case. We're going to assume that X is distributed according to a Gaussian, a normal distribution, with mean mu, which we don't know, and standard deviation, which I will make 1 over square root of 2. I could make it anything. The only reason, any constant. The only reason I make it 1 over square root of 2 is because I'm going to do some math calculation with a Gaussian formula, and it's really convenient when it's 1 over square root of 2. It cancels out the in the exponent. If you ever worked with a Gaussian, it cancels out nicely. So it's just out of laziness that I do this. Now I'm given data, which is x1 through xn, that were all drawn as some IID from this. I'm asked to find the mu, the maximum likelihood mu. To find the maximum likelihood estimate of the mean under these conditions. How do I go about doing that? If you remember, I write down the likelihood function in terms of the known parameters, the unknown parameters, and the data. And then I ask myself what value of the unknown parameters maximizes that expression, given the data. Okay, that's the general formula. Then I do a few tricks. Instead of working on the likelihood function, I look at the log likelihood function, just to help me with finding the maximum. But for the definition of the problem, the definition here is argmax, the value of the unknown parameter mu, that maximizes the likelihood function, and the likelihood function is the likelihood of the data given both the unknown and the known parameters. To do that, I'll write the log likelihood function. Now let me start by writing the entire thing. So what is the likelihood function? Likelihood of the data given the parameters. I use theta as a general parameter, or generalize for all the parameters together. First I use the IID property to say that it's a product of the likelihood of each one of the elements of the data. Likelihood of xi given the parameters. I goes from 1 to n. I use the fact that the data is assumed to come from the same distribution being independently drawn, IID. Nothing here is new. I'm just recaching it into your mind. And now I'm going to write it explicitly in terms of the expression for a Gaussian. So this is a product that goes from 1 to n of 1 over 2 pi sigma. I always forget if the square root goes all the way. I think it doesn't. Square root of 2 pi times sigma. Is that right? It doesn't matter. It's all going to be cancelled out in a minute. Times the x function of minus xi minus mu squared over 2 sigma squared. I just wrote the expression for the Gaussian. Now this is a lot of letters, a lot of Greek. What is important here? Well, since I'm going to take the argmax over mu, what's important is where the mu is. Here's a different color. Everything else is held fixed. Held fixed, but it's still important, so I'll make it green, the xi and the sigma. You see now why it's important to me to hold the sigma fixed. If it weren't fixed, it has an influence in both places. And indeed, you can pose the same problem trying to estimate simultaneously both the sigma and the mu, both the mean and the standard deviation. But the solution is more complicated, because now you have to maximize the two variables. Tom?
What is the likelihood function here? So it's just probability?
It's probability density.
Okay,
yeah. PDF, that's all it is.
I've seen sometimes it's flipped, like likelihood of A given B is the probability of B given A, or something like that.
A and B being the data and the parameters?
Yeah, or just what?
Well, when you're in a discussion of Bayes formalism, all of these things have meaning. So, probability of data given parameters is called the likelihood. Probability of parameters given data is called the posterior. They're different creatures. Posterior is more like a prior, in the sense that probability of parameters given data versus probability of parameters given nothing. They're both the same creatures. One before seeing data, one after seeing data, but they both model the distribution of parameters. As likelihood is a different creature. All I'm saying here is that we have a standard a recipe for maximum likelihood solutions. Write down the likelihood function and now pose the problem, find the maximum of, in this case mu, the value of mu that maximizes this expression. Can we do it in this case? And the answer is yes, we can do it very easily. We use two tricks. One is we look at the log of this rather than at this expression itself. So taking the log of this, we have log likelihood of data given the parameters, and this comes to a sum of the log of the individual likelihood of the individual xi's given the parameters. Which comes to log of this thing, log of 1 over 2 pi sigma, and it's n times, because it's for each one of these, plus sum of the logs of this part, and this is very convenient. Log of this part is just the exponent. So log of the exponent is sum of minus xi minus mu squared over 2 sigma squared. I'm not going to solve this. You were supposed to do it in your homework, just to tell you that the answer, and then take derivative. Take derivative and equate to 0, and you get that the mu maximum likelihood is 1 over n sum xi. This part is constant, it'll go away when you take the derivative, and in fact this doesn't have to cancel out the way I chose it. Any value of this would be fine. It'll go away too at some point. It should all be familiar to you. Now I'm going to do the same thing, but with a different assumption, or a different generating model, a different generating story. The generating story here was that data all came from a single Gaussian that had a fixed mean and a fixed standard deviation. The standard deviation was actually given. The mean was not given, but it's fixed. The story I'm going to give you now is that data comes from a mixture of two Gaussians, each having its own mean and each having its own standard deviation. And the standard deviation are again going to be given, they're going to be the same for both. So they're not an issue. It's a fixed width Gaussian. The only thing that's open is the two means. Two Gaussian, Gaussian A, Gaussian B. Mean mu A, mu B.
Are they equally likely?
That's a very good point. They don't have to be, but for our analysis, to make things simple, I will also assume that they are both equally likely a priori to be chosen to generate the data. So when you see a lot of data, roughly half of it came from the first Gaussian, and roughly half came from the second Gaussian. Or another way of saying it is that the way the data is generated is I take a fair coin, I flip it, if it lands on head, I choose Gaussian A to generate from. If it lands on tail, I choose Gaussian B to generate from. For the second data point, I flip the coin again. So each data point is a separate flip of the coin. So I'm going to repeat the whole process and see where I get stuck. Now I assume mixture of two Gaussians. Which means that X is generated from, I don't know a symbol for a mixture of two Gaussians. I'll invent one. I don't know. Half n of mu A sigma equals 1 over square root of 2 plus half n of mu B sigma equals 1 over square root of 2. So these halves answer your question. They give the prior onto which Gaussian is more likely, or how likely are they to be chosen for each data point. This is just notation. I'm going to give you the exact formal definition when I write down the likelihood function. The likelihood function defines the story. So here's the likelihood function. The likelihood of xi given the model parameters is, you can derive the likelihood from what we call the generative story. Generative story is literally a story of how data is generated. Generative story is directly related to the likelihood function. Sometimes it's easier to understand the assumptions of the model or how data is generated if you talk in terms of a story. First you do this, and you do like the story I gave you with flipping a coin. That's a generative story. So how likely is our model, this current model of mixture of two Gaussians, to generate some particular data point xi? Well, that xi could have been generated if the coin was flipped head or if the coin were flipped on tail. Right? What is the probability was generated if the coin was flipped on head? Well, first there's a probability of 50% that would flip on head. So that would be 1/2. Let me write it more explicitly. First is the probability of it coming, xi coming from A. And then multiplied by the probability of xi given that it came from A. So maybe I'll just write it P of A. Since xi could have come from either A or B, I have to sum over both possibilities. So it'll be P of A times P of xi given A plus P of B times P of xi given B. Or in terms of the generative story, we flip a coin, it has probability of 1/2 of falling on head or on choosing Gaussian A, and if that one was chosen, then xi was generated according to A, which would be 1 over 2 pi squared, square root sigma exp of negative xi minus mu A squared over 2 sigma squared plus 1/2. Exact same story. This 1/2 comes from here. 1 over 2 pi. Exact same story with one difference. minus xi minus mu b. That's our difference. That's mu b squared divided by 2 sigma squared. I used orange here. I'll use orange here too. These are my unknowns, mu a and mu b. These are also parameters, but they're known. And you consider the data is known. And now to find the maximum likelihood, we're talking about a maximum of 2 parameters, mu a and mu b. The maximum likelihood solution is mu a, mu b solution. Mu a, mu b, you can think about it as a vector. Maximum likelihood is those values that maximize over all possible values of mu a, mu b, maximize the likelihood function. Again, theta bar is shorthand for mu a, mu b, and sigma. So far these are exactly the same, except for the form of the likelihood function. And now I'm going to try to do the same thing to actually solve it. So to solve it, this is the likelihood of an individual data point. To get the likelihood of the whole data, I need to multiply them all together. So I have likelihood of all the data, given theta, is a product of the likelihood of individual data points, right? Which is a product of this thing. I don't know if I should write the whole thing with here. Half 1 over 2 pi sigma exp, something with the mu a here, plus half 1 over 2 pi sigma exp, something with mu b here. And I have square brackets here, so I should have a different kind of bracket here. Curly bracket. Does anybody see my problem here? I have a math or arithmetic or calculus problem. I have a product of a sum. How am I going to find the maximum of that? When I was here, I just had a product of a single item. So I could take the log, and that would turn it into a nice sum. And then I could take the derivative of the sum, and lots of things will fall out. Here, if I take the log, a log of this product is a sum of the log of the individual things, but then I end up with a log of this plus this. And a log of sum is not a pleasant, it's not a pretty thing. So I have a very mundane problem. It's not a deep, one way to look at it is it's not very deep. It's just I don't know how to find the maximum. In fact, I don't have an analytical solution. Here, what I did is I derived an analytical solution for the maximum. I could give you a closed form formula that given the xi tells you what the maximum is. Here, I don't believe one exists. That's where my problem starts. What can I do? Try an iterative gradient descent approach. So gradient descent is inherently iterative. Yeah. Try gradient descent. Can we do that? What would it mean? What does it mean to try gradient descent here? Somebody else. Please?
You have to find the derivative of that.
Find the derivative.
Again, gradient descent.
The derivative of the likelihood function.
Yeah.
Okay.
It's still not a trivial thing to do.
It's still not a trivial thing to do. It's hard to see how you can do it analytically. But if you had a finite number of data points, you could just go through them, create this huge expression, and take a small step. So that would mean you start with some mu A, mu B, some random places, and calculate the derivative of the likelihood with regard to small change in the value of the mu A, mu B, as you pointed out, and take a step in the direction. Yeah, you could do that. Is that guaranteed to give you the right answer? No, it's not. Why?
Won't be the global minimum.
It may not be the global minimum. So gradient descent gives you a local minimum, or maximum in this case, because we're talking about likelihood. Gradient descent, so it's gradient ascent in this case, gives you global local maximum. So you should immediately ask yourself, does this function have more than one maximum? You may not know the answer by looking at it, but I can tell you that it has many more than one. So in general, the functions that are hard to find, it kind of goes together. If there's only a single global maximum, it's usually easy to find analytically. Not always, but usually easy to find analytically. If it has many global maxima, once you figure it out, it's hard to find even one of them. So you could try gradient ascent and find a local maximum. Anything else you can do?
I don't know if this makes sense, but can we just pretend they're independent and randomly take half the data and solve it with one, and randomly take half the data and solve it with the
It's a very interesting question. Let's start with the first sentence. You're saying, can we just assume they're independent or pretend they're independent?
Right.
By they, you mean the different data points?
Well, given a data point, I'm not sure which Gaussian it came from.
Right.
And so it seems like there is some kind of dependency.
Meaning, what depends on what? I thought you meant that the choice of which Gaussian they came from for the different data points is independent. You say, maybe that's not what you meant.
I don't think I'm...
Okay, but it's a good direction to go. So the answer is, it is actually independent. The different data points are chosen which Gaussian they're going to come from independently of each other. Does that mean that if we have 1,000 data points, 500 of them came from Gaussian A and 500 from Gaussian B? No. No, each one is drawn independently. About 500 would come from each one, with high likelihood, but we can't be sure. But let's pursue that a little further. So you're saying take our 1,000 data points and kind of pretend for a moment that 500 came from one Gaussian, 500 came from another. Okay? Randomly chosen 500? Okay. Let's try that. So let's say these are two Gaussians. Let's say we knew for a moment what they were. This is Gaussian A and this is Gaussian B. They're meant to be drawn the same height. I apologize. This is A and this is B. Alright, I'll try to make it a little better. And the data points are going to be right here at the bottom. So those that came from A, I'm going to write here. Of course, there are lots in this area and a little bit less here. And those that came from B, there are lots going to be right here and a few here. Okay, this is really busy. and this is a little bit less busy, and there's an overlap here. You can see that. Now, let's imagine these A and B's are thrown out. We only see the data. You could kind of eyeball it and say, I see dense area here and a dense area here, so let's kind of take the center of the dense area and call it and go home, and that's it. Right? You could do that, and probably the answer you get would not be too bad. Of course, the problem is a little harder when the Gaussians overlap even more. But if they don't overlap, if they're really far apart, it's easy. So let's think about that case first. Suppose the Gaussians are very far apart. Then you could take each data point and decide which Gaussian it came from, and you would be correct almost for sure. Right? In this case, for example, this one, we know it came from the leftmost one. We don't care if you call it A or B. Let's say leftmost one and rightmost one. We know this came from the left one. We know this came from the right one. I mean, it's not guaranteed 100%, but it is far more likely that this came from here than from here. If you look at the likelihood ratio, how likely is this to be generated from a mean being here or from a mean being here? Because the Gaussian drops so fast, the dependence of the likelihood and the distance from a mean drops so fast, this is extremely unlikely to have come from here. So if the Gaussians are well separated, one thing we could do is kind of by eye or by common sense assign the points to each one of the Gaussians. Once we assign them, what do we do then? Can you now solve it exactly? Let's say we assign them. We'll give them labels. So we'll call this A. Lots of A's here, and then there's lots of B's here. And, I'm not sure what happens here. Let's just put a line here and say everything to the right is B and everything to the left is A. We won't be right, but let's say we do that. What do we do after that? Please?
Put each half into the singular Gaussian case.
Yes, we're back in the case that we started with. Very simple. We estimate each Gaussian separately from its own data points, and we get the correct maximum likelihood solution for that Gaussian under the assumption that this was how the data points were generated. That's the assumption that's not so kosher. It's not so true. But it won't be a bad assumption either, because most of the time we'll be right, except if they overlap a lot. Okay, so I kind of like that direction. We can even generalize it further. If we were told that the Gaussians were not equally likely a priori, that one of them was 75% and the other one was 25%, the likelihood function here would be 3/4 and 1/4. We could still go to the data and kind of make sure that about 75% of the data points go one direction and the other 25 go the other direction. So we could even do that. Suppose that the data was indeed generated by flipping a coin, and that we somehow were privy to the value of the coin. That somebody told us the flip of the coin. In that case, we could assign each data point with confidence to A or B. Right? So in that case, the assignments would be almost identical, except that here we would be a little smarter. There might be an A on this side, and there might be a B on this side. And who knows, there might even be a point here that we would never suspect it just happened to have come from a B. Nonetheless, if we're told which is which, our job is easy. We now separate it into two independent single Gaussian estimation problem. Let me give this particular notation. Knowing which Gaussian these came from is something we call the latent variable or a hidden variable. It's something that's hidden that we don't usually know. If you use the word hidden, it should remind you of HMMs. It's like the state sequence. In an HMM, you get to observe the symbol that comes out, but you're told a generative story that involves some hidden events that you don't get to observe, but you can reason about them. So hidden events go with latent variables. So now let me tell you what EM is all about. EM is a method for deriving maximum likelihood solutions in cases where the likelihood function cannot be optimized analytically. In particular cases where it cannot be optimized analytically, such as the case here. Now, there are two ways you can think about it. One is just pragmatically. There's a likelihood function that I cannot optimize analytically. I'll give you an iterative procedure for maximizing it nonetheless. The second way to think about it is that there's a generative story involved, usually, that involves some latent variables. The latent variables in our case are, for each data point, was it generated by A or by B? And whenever there's a latent variable story, usually the likelihood function cannot be optimized directly and use EM. So, but it doesn't have to be a latent variable case. Sometimes the likelihood function cannot be optimized directly because some of the data is missing. If you think about a Bayes network, if you remember the story of the fire in the campground and thunderstorms and bus tour group and all of that, sometimes some of the variables, the values are known for some days and others are not. And if you write the likelihood function over many, many days, each day has this combination of a different subset of the variables are known, it is very hard to find the maximum likelihood solution because some of the data is missing. The data may be missing because it's inherently not observable, as in latent variables, or because you didn't bother collecting it, or because the disk was corrupt, or for any reason. Some of the data is missing, turns the likelihood function into an uncomfortable creature that cannot be optimized directly. So let me write that up. EM is a method. I'm not calling it an algorithm for reasons that I will describe later, for deriving maximum likelihood, I'll leave some space here, maximum likelihood solution when the likelihood function is hard to maximize directly. And this could be because of latent variables, or more generally because of missing data. I'm saying more generally because you can think of latent variables as missing data. In the case of the Gaussian, you could say that the entire data is not just the xi's, but also the labels for each xi, whether it came from A or B. And if I'm not told that label, I'm missing some of the data. So you can think about it as a missing data case, or you can think about it as a latent variable case. You can always think of latent variables as variables that you have a right to know, but somebody is withholding them from you. Okay? Or you can just think about them as latent variables. But for these two general cases, the likelihood function is typically hard to maximize. So we're going to use an EM method, and I left space here. It's for the word local. Namely, when we're in this case, it would typically be impossible for us to find a globally maximum likelihood solution. What EM gives us is a local maximum likelihood solution. In that regard, it's very similar to gradient descent. It's designed to search for a maximum because we cannot find it analytically, and it does converge on maximum, although on a local one. It is different than gradient descent in many ways. One is that it typically requires far fewer iterations. Gradient descent often requires thousands of iterations, and it makes very small steps. EM is an iterative procedure that sometimes takes big steps. You don't have to worry about step size. There is no step size in the vanilla formulation of EM. It tells you what step to take and exactly where to go. It's a deterministic algorithm. You start and it automatically tells you what to do. And like gradient descent, it's guaranteed to converge. Gradient descent only guaranteed to converge if the step size is small enough and all that. EM is always guaranteed to converge. One other similarity between the two is that both of them require you to start somewhere. Make a guess where to start. And where you start makes a difference to where you end up. So in gradient descent, you can imagine literally basins of attraction, a basin, where you start somewhere and you follow a gradient and you get to the bottom of that hill. But if you were in a different, or bottom of that valley, but if you're in a different valley, started along the slope of a different valley, you'd end up somewhere else. In EM, it's also somewhat like that. It's harder to see the valleys because it takes steps, big jumps in EM. But nonetheless, conceptually, there is a basin of attraction in EM. Namely, there's a whole bunch of starting points in parameter space that will all end up in the same place, and then a whole bunch of other starting points that will all end up somewhere else. So where you start does determine where you end up. Okay, so this is sort of the conceptual idea. Now, I didn't show you how to do it yet. I'm going to do it now, but I wanted to tell you where I'm taking you. So I'll show you how the EM algorithm operates in the case of our particular example, and we will then generalize. For our particular example, we're going to define the latent variables. We're going to call them ZIA and ZIB. The I goes with the X, XI, ZI. The A and B go with the Gaussians, A and B. And the Z's are latent variables that take on the value only 0 and 1. For any particular I, if ZIA is 1, ZIB is 0, and vice versa. So if the data point XI or X17 came from A, then Z17A would be 1 and Z17B would be 0. ZIA equals 1 if and only if XI came from Gaussian A, and 0 otherwise. And ZIB can be defined simply as 1 minus ZIA. These kind of variables are often called indicator variables or index variables. They are 1 when they want to indicate some event happened and 0 otherwise. You should convince yourself that this definition of the Z's is a very good example of latent variables, in the sense that if we knew the value of the Z's, if our training data consisted not only of x1 through xn, but also of ZIA and ZIB 1 through n, then finding the maximum likelihood solution would be trivial, because it separates the two Gaussians into two separate Gaussian estimation problems. But we don't know their value. So what are we going to do? We're going to write down here, underneath each xi, here are the x's. We're going to write here the appropriate ZAs. ZA, ZB. We can call it x1, x2, x3. We can number them numerically from 1 to n here. This is xn. So this will be Z1A, Z1B, and this would be Z2A and Z2B, all the way to ZNA and ZNB. So now we have 3 rows, x1 to xn, Z1A through Z1n, and Z1B through and B. So for every I we have X, ZA, ZB. And now we can do what you suggested. Remind me of your name? John. What John suggested. We can pretend that we know what the true Z values are by like putting a line here and saying up to here all these will be 1 and these will be 0, and here it will be the other way around. We could do that, but we can do better than that. Instead of assigning them deterministic 0 and 1 values, we can calculate the probability that a particular data point came from A versus from B, based on where it is located. So suppose we had some tentative values of the mu's. So we guessed some values of the mu's. So now we don't know the true mu A and mu B. We guess them, and we will guess them a little different than they really are. Let's say mu A would be here, and mu B will be here. This will be a guess, so I'll put guess. Mu A, mu B. These are tentative guesses. Nonetheless, given these tentative guesses, we can now reason about each data point. How likely is it to belong to A versus how likely it is to belong to B? Right? And then, therefore, we can take these Z values and calculate for them the probability that they are 1 or 0. So I'll give you one specific example, but you can do it for all of them. What is the probability that ZIA is 1? Given specific values of mu A, mu B. These are tentative. It is the probability of ZIA being 1 and XI having come from A. Oopsie. Divide by probability of ZIA is 1 times the same thing, XI having come from A, plus probability of ZIA is 0 and XI having come from B. More qualitatively, if XI is here, the likelihood of it being generated from mu A, which is here, is much larger than being generated from here. So this would go to some large number, let's say 0.8 over 0.8 plus 0.00001, which is this likelihood here. This would account for something that is explained quite well from mu A, maybe here, but very badly by mu B. In the other extreme, when it's explained nicely by mu B, it would be a very small number over a small number plus a large number. What about the things right in the middle? Then these two numbers would be comparable, and you would get 1/2, about 1/2. So given tentative mu's, we could calculate the probability for each one of the z's to be 1 or 0. Instead of thinking about it of the z's as being deterministic, 1 or 0, and having some probability, we can think of them as being fractional. So you can think of each data point, let's say data point here, which is 80% likely came from here and 20% likely came from there. We could think of that data point as if 80% of that data point came from A and 20% of it came from B. The beauty of thinking about it as fractions is that then we can separate the fractions into the A fractions and the B fractions. And we can estimate a new mu A from all the A fractions and a new mu B from all the B fractions. So we'll be back to your idea, John. Except instead of having to insist that every data point is assigned fully to A or to B, we allow ourselves to differentially take each data point and break it into two parts, not necessarily equal. Some of the data point, a fraction of it goes to A, a fraction goes to B. Those data points that are on this side, most of them will go to A. Those that are here, most of them will go to B, and those that are here will go partly A, partly to B. Once we do that, we collect all the fractions into the two separate buckets, A bucket and B bucket, and then we can estimate new mu A and new mu B. The formula for the new mu A and new mu B would be a slight adaptation of this one. This is a standard formula for maximum likelihood from data points, except these are whole data points. We will have to add the weights. There will be a weight here, Wi, for each xi, and there would be a division by the sum of the weights. So we will not need a, oh yeah, we still need a W. But basically that, we would have to do a weighted mean rather than a straight mean. Is this right, what I did here? I think so, yeah. Yeah, these weights go from 0 to 1, so that's here, and you still need 1 over n to find the overall mean. So this is the essence of how the algorithm operates here. You start from some tentative means. You use these means to calculate a posterior over the latent variables. Namely, in our case, what is the probability that any given data point came from A? That's a latent variable. Conditioned on the means. That's why it's a posterior. I'm sorry. Why do I call it posterior? It's not posterior. It's conditioned on the means, conditioned on having some values of the parameters. Take that back. It's not a posterior. It's posterior with regard to knowing the value of the parameters. That's not a posterior. Anyway, we assign some tentative means. We then argue for each data point, if these means were true, how likely is each data point to come from A or from B? And then we fractionate this data point based on that argument. That fraction goes to A, that fraction goes to B. Collect all the fractions separately, re-estimate the means. Once we re-estimated the means, we need to go back and reassign each data point. Because now that the means are different, the data points may be assigned differently. Once we reassign them, we refractionate them, recalculate the means. Again and again and again. What we're guaranteed is that the likelihood function will keep increasing every time we do that, until it reaches a local maximum. This gives us the local maximum. Questions so far? Okay, after all this hand waving, let me show you some slides. By the way, the algorithm I described now can be very easily generalized to, instead of 2 Gaussians, any number of Gaussians, k Gaussians. Instead of having ZA and ZB, we will have ZA, ZB, ZC, ZD all the way to ZK. As many rows of Z's as there are Gaussians in the mixture. And you have to start with some choice for each one of the k means. and then iteratively fractionate the data into k different buckets. When you do that, the algorithm is called k-means. The k-means algorithm. Sorry. So here is the two Gaussians, and much nicer picture than I'm able to draw. You can see the two Gaussians, you can see their overlap, and you can see the data points at the bottom. Here you see the generative story. Each instance k is generated by first choosing one of the k Gaussians, even though in the picture there are only two, but in principle they're k. And here they chose with uniform probability, just like I chose half and half, but it doesn't have to be. And in fact, there's a version of the EM algorithm where the prior on with what probability you choose which Gaussian is also up for grabs, and you're jointly maximizing. It's also a parameter, and you can jointly maximize that prior with the means. And there's yet another version of EM where you jointly maximize the prior, the means, and the standard deviations. So we just chose the simplest case where the prior was known and happened to be uniform, and the standard deviation was known. So we're only optimizing the means. But EM could be used when all of them are not known. And after you choose a Gaussian, you generate an instance according to that Gaussian. And here is the formula. So the formula I write on the board are sometimes a little sloppy if you want to be sure that you have it right. A word about why it's called EM. I'm missing the explanation here. It's called EM because it consists of alternating two steps. An E step, oops, the E and the M were just stripped off here and here. Should be E and M. The E step is the calculation, given some tentative value of the parameters, of the expectation of the latent variables. The expectation of the latent variables, what is an expectation of a index latent variable? A binary variable. What is the expectation of ZIA? It's basically the probability that ZIA is 1. Right? Because ZIA can only be 1 and 0. So to say what is the expectation of ZIA, it's exactly the same as what is the probability that it's 1. So in the E step we calculate the expectation of the latent variables, namely the probability that they are 1, or in other words, which fraction of the data point should go into each bucket. So here's the formula for which fraction of ZIA should go into the jth bucket. In the M step, you take each bucket separately and you estimate a maximum likelihood solution for that bucket, assuming that these fractions are correct. It's called M for maximizing. You maximize the value of mu for that bucket or for that Gaussian given the tentative fractions. And this is the formula that I mentioned to you. It's a summation, a weighted average of the xi's weighted by the fractions. These are the fractions that went into the different buckets. So we start somewhere by assuming values of the mu's, then we go through the E step, calculate fractions, then the M step, re-estimate the means. E step, M step, E step, M step. Keep doing that typically until there's no more change in the value of the parameters from one step to the other. In practice you have to be a little careful. There can be extreme unusual cases where the values keep changing but the likelihood function doesn't change. Theoretically, what the algorithm guarantees you, what the math guarantees you, is not that the parameters stop changing, but that the likelihood stops growing. It goes up and up and up and then it asymptotes. So you can keep track of the likelihood instead. and stop when it doesn't change much anymore. Does this look even a little bit familiar to the learning we did in hidden Markov models? Do you remember the forward-backward algorithm? We calculated the alpha table, we calculated the beta table, from this we calculated the gamma table, and then we re-estimated the A's and the B's, the transition and emission probabilities. And if you remember, the way the whole learning algorithm there works is you start with some transition and emission probabilities, A and B matrices. Then based on that you tentatively calculate the alpha, beta and gamma tables. These are basically the latent variable calculation. And then you use that, we had re-estimation formulas for re-estimating the A's and the B's based on the expected number of times you see transitions from state I to state J at time t and so forth. This is exactly what's going on here. That re-estimation was the M step. The building of the alpha, beta and gamma table was the E step. Any questions? So, this is somewhat oversimplified. It's true. Everything I said is hopefully correct. But it's simplified in the sense that the EM algorithm is very general and it will not always be as easy to derive as it was here. For the vast majority of problems that we run into, where the likelihood function falls into a very general class of distributions called exponential distributions, EM algorithm always boils down to identifying those latent variables and collecting fractional points for them and then re-estimating. And for most things you'll run into, that would be enough. It turns out the EM algorithm is more general than that. And there are situations where it doesn't boil down to just collecting fractional counts, but it's still the EM algorithm. So I want to give you, just for completeness, the general form of the EM algorithm. It actually involves much less math than this. But now that you got the general idea from here, it'll be easier to understand what I'm talking about. So we'll do it here. So in the general case, you have partial data. Namely, you have some of the data, and some of the data is hidden or missing. And there is typically a notation for the data. The notation is very confusing because it uses X and Y in a way that we're not used to. So I just want to warn you about that. I think the book follows the standard notation. We used X for our observable data because we usually use X for data. But when you deal with EM, usually we use Y for the observable part of the data. So, observed data is Y. Missing or hidden data or latent Z. And I'll give you a term that you might run into, you should know what it means. Complete data is X, which consists of Y and Z. So if you ever see papers that deal with EM, they typically would use this notation. Sometimes people will fudge and will use X for this standard observable like we did today. Z is almost always reserved for the hidden. Let's see what the book uses. No, the book uses the more the book uses the more intuitive thing that we've been using here. So I'll do that too. The original paper on EM uses this. The book uses what I would prefer to use, which is that the observed data is X, and therefore this is Y and Z. I apologize for the confusion. Just keep in mind that whenever you look at the data, you need to know which is used for what. There's observed, hidden, and together they form the complete. So I'll stick to that. Okay, now our goal is to find the maximum likelihood of the complete data. So the goal is to maximize probability, and we said the complete is Y, of Y given the parameters. Now again, for the parameters I can use my favorite, which is theta. I'll do that. I'm not sure what the book uses. In HMMs we use lambda, not the parameters. Now our problem starts with the fact that Y consists of an observed part and an unobserved part, and we don't know what the unobserved part is. If we knew the observed part, it would be trivial. The unobserved part, the hidden part, we don't know what it is. So first of all, I'm going to switch from maximizing the likelihood to maximizing the log likelihood. Here's what I'm going to do. I'm going to say, pretend that just for the purpose of generating the data that I saw, theta was fixed at some value. If theta was fixed at some value, that is the tentative values of the means in our examples, that forms some distribution over the z's, over the unknown parameters. Right? So if theta, I'll call it theta prime, is fixed, that leads to a distribution based on theta prime of y and z, this is x and z. Distribution over z. For a given x, z has a certain distribution. This corresponds to, for a given data point in the mixture of two Gaussians, the z's have some values of which Gaussian it came from. In our case, it was a binary value. It came from A or it came from B. But in general, Z would have some distribution. So if it has a distribution, I can get the log of this. I can think in terms of taking the expected value of the log of this over that distribution. So first let me write this as log of P of X and Z given theta. X and Z together are Y, and then I'm going to convert that into an expectation. It's an expectation over the variable Z. Since I don't know what Z is and I will never know what Z is, I'm treating it as a random variable to take expectation over, to average over, under some assumption of theta prime. So this is how I write it. It's going to be an expectation of the quantity I'm interested in, which is the log likelihood, log complete likelihood, Expectation taken over the unknown part that can vary. But I have to start somewhere, so I'm going to assume that it varies based on some tentative values of the parameters. So now I have P of x and z given theta. I'm sorry, there's a log here. Okay, now what am I doing? Now I'm trying to, remember all I'm trying to do here is to find the value of the theta that maximizes this. Now I have to be careful between two thetas. This is fixed. This is a initial tentative guess. This is what I'm trying to maximize. This is often written as expectation of the log of P of x and z given theta conditioned on the tentative theta. I wrote the same as here, I just made the dependence, I wrote it in a more explicit way. The expectation is calculated based on some tentative values of the parameters, but this is still free, a free parameter, and I'm going to look for the argmax of that, of this theta. And that's going to be my new theta. So my new theta, theta of iteration k plus 1 equals to this calculation over theta of iteration k. So now I gave you the entire AEM algorithm in one equation. Start with some theta 0. Plug it here as an overall condition there. This determines the distribution here. Specifically how z varies. Because P of x and z can be written as P of x times P of z given x. But P of z given x depends on the tentative parameters. In our case of the Gaussians, P of x is very simple, it's just a Gaussian formula, that exponential. P of z given x is the probability, z is the latent variable, the probability that that data item came from Gaussian A, given what the data item is, but also given what the two mu's are. Right? So this is needed to understand the dependence of the hidden, how the hidden variable value is distributed given x. But once it's used here, this one is still left free. This is really the parameters we're optimizing over. Theta. This is the free theta, free argument. Whereas this is just a conditioner. Now this one formula captures both the E step and the M step. The E step is calculating this part. The M step is doing the maximization. You will also see this written in a slightly different form. This entire function will be called Q, and I think Q has only theta and theta prime, yeah. Q of theta and theta prime. And I think the book might use theta prime to say what I call theta, and theta to say theta prime. But that's just notation. The important thing is which one is the formal variable and which one is the tentative assumption. This is called an auxiliary function. And it captures this whole thing here. It just shows explicit dependence on these two. I'm mentioning these terms to you because you might run into them in some other context. You should see the relationship. And also because it opens the way for even further generalization, and that is the auxiliary function does not have to be expectation of the log likelihood. It could actually be something else. Remember that my goal was maximizing the likelihood, and I end up working with the log likelihood. I could have put a different function here, not just log. In fact, I could use any convex function, and it would work fine. Have you heard of Jensen's inequality? Yes? Okay. So Jensen's inequality is very important. It's actually used in the proof of the correctness of the EM algorithm. And Jensen's inequality applies every time you have a convex function, like log. If we have time, I guess we have 5 minutes, we can discuss it unless we have other questions. I owe you one more explanation. I wrote here that EM is a method, and I didn't write the word algorithm. And the reason is, even though people typically talk about the EM algorithm, it's really not correct. An algorithm, by its very definition, is a very well-defined, explicit sequence of steps that a computer can follow. That means there's no ifs, ands, and buts, there's no ambiguity, it's clear what you should do. The EM method is not an algorithm because sometimes it's not clear how you use it. All I'm telling you is that you have to write this expression and then maximize it. Well, what if the form of the likelihood function is so convoluted that finding the expectation is difficult or intractable, or you don't know how to do that? Or what if finding the maximum is difficult or intractable? You don't know how to do. So I'm just giving you a recipe saying find the expectation and find the maximum of the expectation, then find the expectation and find the maximum. But if you're in a situation where doing that is not feasible, then you cannot use the EM algorithm. And there are many situations where people try to derive EM algorithms for particular problems, and sometimes they succeed and sometimes they fail, depending on whether they can do the E and the M steps. The M step is usually easier, but not always. Sometimes you get stuck on the M step. So a very common thing that you see is people describe a model or a situation and they say, oh, this looks like a latent variable model, here's the EM algorithm I derived for it. That means they went through this process. Questions? Tom?
You're referring to the proof of why EM wants convergence?
Mm-hmm.
So which function is it that actually needs to be convex?
This function.
The log or the log?
The log. The log is a function which could be convex. The likelihood function does not need to be convex for EM. Right. Right. But what I'm saying is you can generalize, you can have other non-EMs or generalizations of EMs that don't use log, they use something else.
Okay.
It's also convex. So let me use the last 4 minutes to talk about Jensen's inequality. Imagine a convex function of a single variable. It's convex, so it looks like this, and mathematically it's defined as the second derivative is negative. Right? Now imagine the definition of a convex function is if you pass a line, this entire function is above the line. Wherever the line, if the line hits 2 points, the function is above that 2-point line. Take a point here and the function above it. That point is a weighted sum of these points, A and B. So one way to write the value of this point, the y value of this point, is first you take, I'm sorry, this is B and this is A and this is f of A and this is f of b. And this point is at distance w between a and b. So it's w to here, and 1 minus w here. Okay? Or let's call it WA and WB, and they sum to 1. The important point is that the y value here can be written as WA times f of A plus WB times f of B divided by WA plus WB. It is basically a weighted sum of f of A and f of B. Whereas the point here is f of WA times A plus WB times B divided by WA plus WB. So compare these two. This is a weighted sum of the function values. This is a function of the weighted sums. Okay? Do you do the weighting on the function value, or do you do the weighting on the argument? In the general case, you would have f of some Wi xi compared with some Wi f of xi. I'm assuming that Wi is sum to 1. This is the general case of many data points. A convex function, this is always greater than this, greater or equal. This is greater or equal. Now, it's a small step from this to say if the Wi's sum to 1, it's like expectation. You can think of expectation as a sum, sometimes an infinite sum. So this becomes f of the expectation of x compared to the expectation of f of x. See the relationship? The weighted summation can be thought of as expectation. And the f of is always greater for f convex. So if f is convex, this is always true. Now take the log function, the simple log of a single variable. If f is the log function, f is the log of something, then log of the expectation is greater than or equal the expectation of the log. This is the fundamental formula that is used in proving that EM converges. You write the likelihood function before the iteration and the likelihood function of the iteration, and you do some algebra, and you end up with something like log, expectation of log or log of expectation. There's a crucial step there where you can invert the two based on Jensen inequality. It goes only in one direction, not in the other direction. But you could do it not just with a log function, you could do it with any convex function. Questions? Okay, thank you.